Welcome back. 4 modules down, 2 to go in this course. Great work so far. In the last lesson, we learned how to partition and set up disks with file systems to start storing files. We also dove deeper into the details of file systems and even learned tools for repairing corrupt file systems and disks. In this lesson, we're going to talk about processes. Processes play an important part in our computer user experience. After all, why use a computer if you can't use any programs? With more and more processes running on our computer, we have to think about ways to better utilize our hardware resources. Get ready, because we're going to get into the nitty-gritty of processes. We'll talk about how to read process output and learn how to track our resources. Ready? Set? Let's go! In an earlier lesson, we learned that programs are the applications that we can run, like the Chrome web browser. Processes are programs that are running. We can have lots of processes running for the same program, like how we can have many Chrome windows open at once or lots of movies playing using one program. When we launch a process, we're executing a program, and remember, a program is just software. To calculate the information that our software contains, we need to give it resources so that it can be run. When processes are run, they take up hardware resources like CPU and RAM. Luckily, today's computers are powerful enough to handle the processes that we use in our day-to-day activities, like browsing the web, watching movies, etc. But sometimes this isn't enough. Sometimes a process is taking more resources than it's supposed to. Sometimes processes are unresponsive and freeze up our system, making our entire computer unresponsive. Well, we're going to talk about why this happens and how we can fix it in the upcoming lessons. But before we can talk about managing processes, we have to understand how they work. When you open up an application like a word processor, you're launching a process. That process is given something called a process ID to uniquely identify it from other processes. Our computer sees that the process needs hardware resources to run, so our kernel makes decisions to figure out what resources to give it. Then, in the blink of an eye, our computer starts up a word processor, and ta-da! We're ready to start working. This happens for every process you launch yourself and for every process you don't even know is running. Besides the visible processes that we start, like our music player or word processor, there are also not-so-visible processes running. These are known as background processes, sometimes referred to as daemon processes. Background processes are processes that run in the background. We don't really see them, and we don't interact with them, but our system needs them to function. They include processes like scheduling resources, logging, managing networks, and more. When we take a look at all the processes running on our system, you'll see what I'm talking about. In the next couple of lessons, we'll talk about how processes get created and terminated. Then, we can start digging into the details of process management. Process management is a vital skill in IT support. You'll often find yourself troubleshooting issues with frozen applications, slow applications, and more. The way that processes are created and stopped differs based on the operating system you use. First, let's have a look at how Windows does things. When Windows boots up or starts, the first non-kernel user mode that starts is the Session Manager Subsystem, or SMSS.exe. The SMSS.exe process is in charge of setting some stuff up for the OS to work. It then kicks off the login process, called winlogon.exe, appropriately enough, along with the client-server runtime subsystem called CSRSS.exe, which handles running the Windows GUI and command line console. We'll talk about a process called init in the next lesson, which Linux uses as the first process. You might be tempted to think of SMSS.exe as the Windows equivalent of init. Don't fall into that trap, though. When it comes to process creation mechanisms, they're all pretty different. In Windows, each new process that's created needs a parent to tell the operating system that a new process needs to be made. The child process inherits some things from its parent, like variables and settings, which we can collectively refer to as an environment. This gives the child process a pretty good start in life, but after the initial creation step, the child is pretty much on its own. Unlike in Linux, Windows processes can operate independently of their parents. Let's take a look at how this works by creating our own. First, let's launch the PowerShell process to give us a Windows command prompt. From there, we can type in notepad.exe to create a new process for the Notepad program. So far, so good. The parent process is PowerShell, and the child is the Notepad application. What happens if we kill the parent process, though, by clicking on the X button? Notice that Notepad keeps on running happily, even though its parent has been terminated. Those children are just in their own world. Clicking the X is just one way to stop a process from running in Windows. But as you might expect, there are other ways you can stop processes. You can use a command prompt command by calling on the task_kill utility. Task_kill can find and halt a process in a few ways. One of the more common ways is to use an identification number known as the process ID or PID to tell task_kill which process you'd like stopped. One way to do this is to kill Notepad again by specifying the PID using task_kill/PID and then the PID number. So task_kill/PID. This is the process ID of Notepad. And success! This will send the termination signal to the process identified by the PID, which happens to be Notepad in our case. This is useful, but how do we get that PID in the first place? Glad you asked. We'll talk about how to locate and view processes and other more detailed process information in an upcoming lesson. In Linux, processes have a parent-child relationship. This means that every process that you launch comes from another process. Let's check out this command. The less command would be the parent process to our grep process. If all processes come from another process, there must be an initial process that started this all, right? Yes, there is. When you start up your computer, the kernel creates a process called init, which has a PID of 1. Init starts up other processes that we need to get our computer up and running. There are more nuances to process creation than this, but I wanted to introduce the parent process concept since you'll see them when we start managing processes. What about what happens when we're done with our processes? When your processes complete their task, they'll generally terminate automatically. Once a process terminates, it'll release all the resources it was using back to the kernel so that they can be used for another process. You can also manually terminate a process, which we'll discuss how to do in an upcoming lesson. It might feel like we're starting to get into the weeds here, so let's take a step back and think about what processes really are and what they represent in the context of an operating system. You can think of processes as programs in motion. Consider all the code for your internet browser. It sits there on your hard drive, quietly waiting for its time to shine. Once you start it up, the operating system takes that resting code, then turns it into a running, responding, working application. In other words, it becomes a process. You interact with, launch, and halt processes all the time on computers, although the OS usually takes care of all that behind the scenes. By learning about processes, you're taking a peek behind the curtain at how operating systems really work. This knowledge is both fascinating and powerful, especially when applied by a savvy IT support specialist to solve problems. Keep all that in mind as we take a look at how you can pull back the curtain even further. Next, we'll learn about the different ways you can investigate which processes are running on a Windows computer and more methods of interacting with them. On the Windows operating system, the Task Manager or taskmgr.exe is one method of obtaining process information. You can open it with the Control-Shift-Escape key combination or by locating it using the Start menu. If you click on the Processes tab, you should see a list of the processes that the current user is running, along with a few of the system-level processes that the user can see. Information about each process is broken out into columns in the Task Manager. The Task Manager tells you what application or image the process is running, along with the user who launched it and the CPU or memory resources it's using. To kill a process, you can select any of the process rows and click the End Task button in the lower right corner. We can demonstrate this by launching another notepad.exe process from the command line, then switching over to the Task Manager, selecting the notepad.exe process, and ending it. I already have Notepad open, so I'm just going to click on it, click End Task. In an earlier lesson, we talked about starting and ending Windows processes. Remember that we used the task kill command to stop a process by its identification number, or PID. So how do we get that PID number? Well, in Task Manager, you can click on the Details menu option. In here, you can see a whole bunch of other information you can get the Task Manager to display, including the PID. You can also see this information from both the command prompt and PowerShell. From the command prompt, you can use a utility called Task List to show all the running processes. From a PowerShell prompt, you can use a commandlet called get-process to do the same. There are lots of ways you can get process information from the Windows operating system. We've included links to the documentation of both task lists and get-process in the supplementary reading in case you want to dive deeper into either of these tools. Okay, now let's talk about how to view the processes running on our system in Linux. We'll be using the ps command, so let's just go ahead and run that command with the -x flag and see what happens. This shows you a snapshot of the current processes you have running on your system. The ps output can be overwhelming to look at at first, but don't worry, we'll walk through how to read this output. Let's start from right to left here. PID or PID is the process ID. Remember, processes get a unique ID when they're launched. TTY, this is the terminal associated with the process. We won't talk about this field, but you can read more about it in the man pages linked right after this video. Stat, this is the process status. If you see an R here, it means the process is running or it's waiting to run. Another common status you'll see is T for stopped, meaning a process that's been suspended. Another one you might see is an S for interruptible sleep, meaning the task is waiting for an event to complete before it resumes. You can read more about the other types of process statuses in the man pages. Time. This is the total CPU time that the process has taken up. And lastly, command. This is the name of the command we're running. Okay, now we're going to enter hard mode here. Run this command, ps-ef. The E flag is used to get all processes, even the ones run by other users. The -f flag is for full, which shows you full details about a process. Look at that! We have more processes and even more process details. Let's break this down. UID is the user ID of the person who launched the process. PID is the process ID. And PPID is the parent ID that we discussed in an earlier lesson, which launched the process. C is the number of children processes that this process has. S time is the start time of the process. TTY is the terminal associated with the process. Time is the total CPU time that the process has taken up. And CMD or command is the name of the command that we're running. What if we wanted to search through this output? It's super messy right now. Can you think of a way we can see if a process is running? That's right, with the grep command. I told you we were going to use it all the time. This will give us a list of processes that have the name Chrome in them. There's another way to view process information. Remember, everything in Linux is a file, even processes. To view the files that correspond to processes, we can look into the /proc directory. There are a lot of directories here for every process that's running. If you looked inside one of the subdirectories, it'll give you even more information about the process. Let's look at a sample process status file for PID 1805. This tells us even more information about a process state than what we saw in PS. While the /proc directory is interesting to look at, it's not very practical when we need to troubleshoot issues with processes. For now, stick with the ps-ef command to look at process information. As you can see, we can learn a lot about the processes running on our machine with just a few keystrokes. In an upcoming lesson, we'll talk about how to use process information to our benefit when figuring out which processes are taking up too many resources. For now, feel free to learn a little more about the processes that you're running. I'll be waiting for you in the next video. Imagine you're starting up a video game that's taking a while to render its graphics. You decide that you don't want to play anymore, which leaves you with a few options. You can wait for it to finish loading and then quit the game from the menu, or you can interrupt the process altogether, telling it to quit at the system level. This is just one example of a time you might find yourself wanting to close a process before it fully completes. To tell a process to quit at the system level, we use something called a signal. A signal is a way to tell a process that something's just happened. You can generate a signal with special characters on your keyboard and through other processes and software. One of the most common signals you'll come across is called SIGINT, which stands for Signal Interrupt. You can send this signal to a running process with the Control-C key combination. Let's say you start up the DiskPart tool we looked at in our discussion on partition formatting. I'm just going to open up Command Prompt and then launch DiskPart. If you decide you don't want to actually format any disks, you can hold down the Control key and press C at the same time to send the SIGINT signal to the DiskPart process. You'll see that the window that the DiskPart program was running in closes and the process terminates. There are a few other Windows signals that processes can send and receive. But unlike in Linux, there isn't an easy way for an end user to issue arbitrary signal commands. If you're interested in learning more about Windows signals, check out the signal reference link in the supplementary reading. In Linux, there are lots of signals that we can send to processes. These signals are labeled with names starting with SIG. Remember the SIGINT signal we talked about before? You can use SIGINT to interrupt a process, and the default action of this signal is to terminate the process that it's interrupting. This is true for Linux too. You can send a SIGINT signal through the keyboard combination Control-C. Let's see this in action. I'm going to do the same thing as we did in Windows and start a program like sudo parted. We can see that we're in the parted tool now. Let's interrupt this tool and say we want it to abort the process with the Control-C keyboard combination. Now we can see that the process closed and we're back in our shell. We were able to interrupt our process midway and terminate it. Success! There are lots of signals used in Linux, and we'll talk about the most common ones in the upcoming lessons. In earlier lessons, we talked about processes. We saw some examples of how to manipulate them with signals. Let's expand on that idea of process management by looking at some other things you can do to manipulate processes. In Windows, we've looked at programs like Task Manager, the PowerShell commandlet get-process, and the task list utility, to name a few. We've also seen how to send a running process a signal through Control-C. But there's another process management tool we haven't talked about, which lets you do things like restart or even pause processes. This tool is called Process Explorer. Process Explorer is a utility Microsoft created to let IT support specialists, systems administrators, and other users look at running processes. Although it doesn't come built into the Windows operating system, you can download it from the Microsoft website, which I've linked to in the supplemental reading right after this video. Once you've downloaded Process Explorer and started it up, you'll be presented with a view of the currently active processes in the top window pane. You'll also see a list of the files a selected process is using in the bottom window pane. This can be super handy if you need to figure out which processes use a certain file, or if you want to get insight into exactly what a process is doing and how it works. You can search for a process easily in Process Explorer by either pressing Ctrl+F or clicking on the little binocular button. Let's go ahead and do a search for the Notepad process we opened up earlier. You should see C/Windows/System32/Notepad.exe listed as one of the search results. If you see something that says Notepad.exe.mui, don't worry. MUI stands for Multilingual User Interface, and it contains a package of features to support different languages. Anyways, once you've located the Notepad.exe process, notice how it's nested under the Command.exe process in the UI. This indicates that it's a child process of Command.exe. If you right-click on the Notepad.exe process, you'll be given a list of different options that you can use to manage the process. Check out the ones that say Kill Process Tree, Restart and Suspend. Kill Process does what you might expect. Say goodbye to Notepad. Kill Process Tree does a little bit more. It'll kill the process and all of its descendants, so any child process started from it will be stopped. Kill Process Tree takes no prisoners. Restart is another interesting option. You might be able to guess what it does just by its name. It'll stop, then start the process again. Let's do that with the Notepad.exe process we started from Command.exe. Interesting, after the restart, Notepad.exe doesn't appear as a child of Command.exe anymore. What gives? Well, if we search for Notepad.exe again, we can see it's been restarted as a child of the procexp.exe process. This is the process name for Process Explorer. This makes sense since Process Explorer was the process in charge of starting it again after we terminated it. But what about the suspend option? Instead of killing a process, you can use this option to suspend it and potentially continue it at a later time. If we right-click Suspend the process, we'll see that in the CPU column of Process Explorer output, the word suspended appears. While a process is suspended, it doesn't consume the resources it did when it was active. We can kick it off again by right-clicking and selecting the Resume option. Process Explorer can do a lot, and we'll take a look at some of the monitoring information it can give us in an upcoming lesson. We won't get into the details of all its features though, so if you're curious, you can check out the documentation on Microsoft's website. We put a link to it for you in the supplementary reading. Let's talk about how to use signals to manage processes in Linux. First up, terminating processes. We can terminate a process using the kill command. It might sound a bit morbid, but that's just how it is in the dog-eat-dog world of terminating processes. The kill command without any flags sends a termination signal or sig_term. This will kill the process, but it'll give it some time to clean up the resources it was using. If you don't give the process a chance to clean up some of the files it was working with, it could cause file corruption. I'm going to keep a process window open so you can see how our processes get affected as we run these commands. So to terminate a process, we'll use the kill command along with the PID of the process we want to terminate. Let's just go ahead and kill this Firefox process. And if we check the process window, we can see that the process is no longer running. The other signal that you might see pop up every now and then is the sig_kill signal. This will kill your process with a lot of metaphorical fire. Using a sig_term is like telling your process, "Hey there process, I don't really need you to complete right now, so could you just stop what you're doing?" And using sig_kill is basically telling your process, "Okay, it's time to die." The signal does its very best to make sure your process absolutely gets terminated and will kill it without giving it time to clean up. To send a sig_kill signal, you can add a flag to the kill command, -kill for sig_kill. So let's open up Firefox one more time. So kill -kill 10392. And now you can see that Firefox has been killed. These are the two most common ways to terminate a process, but it's important to call out that using kill-kill is a last resort to terminating a process. Since it doesn't do any cleanup, you could end up doing more harm to your files than good. Let's say you had a process running that you didn't want to terminate, but maybe you just want to put it on pause. You can do this by sending the sig_tstop signal for terminal stop, which will put your process in a suspended state. To send this, you can use the kill command with the flag -tstop. I'm going to run ps-x so you can see the status of the processes. We're just going to put this process in a suspended state. So kill-tstop 754. Now you can see the process 10754 is now in a suspended state. You can also send the sig_tstop signal using the keyboard combination Ctrl+Z. To resume the execution of the process, you can use the sig_cont for continue signal. Let's go ahead and look at the process table again. I'm going to go ahead and use that command on this process. Now if I look at the process again, you'll see that the process status turned from a T to an S. Sig_term, sig_kill, and sig_tstop are some of the most common signals you'll see when you're working with processes in Linux. Now that you have a grasp on these signals, let's use them to help us utilize hardware resources better.
In mobile operating systems like iOS and Android, you won't be able to see a list of running processes. Instead, you'll manage mobile apps that are running on the OS. When a mobile app is running, there will be one or more processes associated with them, but those details will be managed by the OS. Let's take a look at how you can manage your running mobile apps and understand how they're using your mobile device's resources. As an IT support specialist, you may help end users to troubleshoot slow mobile devices and manage their mobile apps. We'll show you examples of what you might see, but you may have to refer to your device's documentation if it doesn't look like these examples. First, let's check what apps are currently running on our device by opening the App Switcher in iOS. From the App Switcher, I can see a list of apps running on this iPhone. Now let's do the same thing in Android. Great. Each of the apps that I have launched is listed here. I can scroll through this list and switch to an app by tapping it. Now I can use this calculator. The app that we're using is called the foreground app. All of these other apps are in the background. What do you think is happening with the background apps while I'm calculating how many bits are in this megabyte? The details can be a little complicated, but the basic idea is this. As soon as it can, the OS will suspend background mobile apps. A suspended app is paused but not closed. The OS can occasionally wake a backgrounded app to allow it to do some work, but it will try to keep apps suspended as much as it can. Let's go back to the home screen. Now that I'm on the home screen, all of the apps are backgrounded, and there are no foreground apps. The calculator hasn't been closed. Each new app that you open will be kept backgrounded and usually suspended. This helps the device use less battery power. And pro tip, as an IT support specialist, it's pretty helpful to learn which apps on your mobile device use the most battery power. If you have an app that the OS can't suspend because the app keeps working in the background or it's frozen, then that can slow your device and use up battery. IT support specialists often have to find these misbehaving apps and close or uninstall them. Let's try closing some of the apps. From the iOS app switcher, we can swipe up on any of the background apps. This will close the app. We can do the same thing in Android. In this version of Android, we can also swipe over here and hit Clear All to close all of the apps at once. You can troubleshoot a misbehaving app by closing apps one at a time and seeing if there's one app in particular that slows the device down. Sometimes closing a misbehaving app will be all you need to do to make your device run smoothly again. Start with the app that's currently being used and see if that helps. The app switcher shows you the apps in order from most recently used to least recently used. Work backwards through time, trying one app at a time. Remember that this is not something that you should have to do very often to make your device work properly. With current versions of iOS and Android, you shouldn't ever have to close an app for performance reasons unless the app is misbehaving. It can actually use up more battery to close and reopen an app than it would if you had just left it running. If you discover that you have an app that's routinely misbehaving, you can try resetting it completely by clearing its cache, like we saw in an earlier video. If the device is still running sluggishly after closing all of the apps, the next thing to try is to simply restart the device. And if restarting the device doesn't fix the performance issues, or it's only a temporary fix, then we need to dig deeper. Let's check the battery use of the apps that we've installed. On the iPhone, I go to the Settings app, then Battery Health. Here, I can see how quickly the battery's been used since the last charge. I can also see which apps are using the most battery. Let's look at the same settings in Android. Again, I go to the Settings app, and from here, I'll choose Battery, then More, then Battery Usage. From here, I can see which apps are using the most battery. If I see an app that's using a lot of battery, then it might not be working as it should. Or maybe it's an app that uses a lot of battery to work. You'll need to learn which apps the end user needs to know whether or not the battery use is unusual.
You've been doing a great job, and we're almost done with this module. Okay, now that we've spent all this time learning about processes, like how to read them and how to manage them, when are we ever going to use these newfound skills? Well, pretty much all the time. But in an IT support role, managing processes comes in handy the most when processes become a little unruly. Our systems usually have some pretty good ways of monitoring processes and telling us which processes might be having issues. In Windows, one of the most common ways to quickly take a peek at how the system resources are doing is by using the Resource Monitoring tool. You can find it in a couple places, but we'll launch it right from the Start menu. Once it opens, you'll see 5 tabs of information. One is an overview of all the resources on the system. Each other tab is dedicated to displaying information about a particular resource on the system. You'll also notice that Resource Monitor displays process information too, along with data about the resources that the process is consuming. You can get this performance information in a slightly less detailed presentation from Process Explorer. Just select the process you're interested in, right-click, and choose Properties. From there, pick the Performance Graph tab. You can see quick visualizations of the current CPU, memory, indicated by private bytes, and disk activity, indicated by I/O. But how can we get this information from the command line? I'm glad you asked. There are several ways to get this information from the command line, but we'll focus on a PowerShell-centric one, our friend get-process. We know that if we run get-process without any options or flags, we get process information for each running process on the system. If you check out the column headings at the start of the output, you'll see things like npm-k values in this column represent the amount of non-paged memory the process is using, and the K stands for the unit, kilobytes. You can see Microsoft's documentation for a full write-up of each column in the next supplemental reading. This is useful, but it's a lot of information. It can be really helpful to filter down to just the data you're interested in. Let's say you wanted to just display the top 3 processes using the most CPU. You could write this command. Get-process pipe sort CPU descending pipe select -first 3 -property ID process name and CPU. And just like that, we get the top 3 CPU hogs on the system. This command might be a little hard to understand, so let's go through it step by step. First, we call the get-process commandlet to obtain all that process information from the operating system. Then, we use a pipe to connect the output of that command to the sort command. You might remember pipes from some Linux examples earlier. We sort the output of get-process by the CPU column, descending to put the biggest numbers first. Then, we pipe that information to the select command. Using select, we pick the first 3 rows from the output of sort and pick only the property ID, name, and CPU amount to display. Now that you've got some knowledge about both the command line and graphical tools Windows provides for investigating resource usage, let's have a look at Linux resource monitoring. A useful command to find out what your system utilization looks like in real time is the top command. Top shows us the top processes that are using the most resources on our machine. We also get a quick snapshot of total tasks running or idle, CPU usage, memory usage, and more. One of the most common places to check when using the top command are these fields here, %CPU and %mem. This shows what CPU and memory usage a single task is taking up. To get out of the top command, just hit the Q key for quit. A common situation you might encounter is when a user's computer is running a little slow. It could be for lots of reasons, but one of the most common ones is the overuse of hardware resources. If you find that a top shows you a certain task is taking up a lot of memory or CPU, you should investigate what the process is doing. You might even terminate the process so that it gives back the resources it was using. Another useful tool for resource utilization is the uptime command. This command shows information about the current time, how long your system's been running, how many users are logged on, and what the load average of your machine is. From here, we can see the current time is 16:43 or 4:43. Our system has been up for 5 hours and 8 minutes, and we have 1 user logged in. The part that we want to talk about here is the system load average. This shows the average CPU load in 1, 5, and 15-minute intervals. Load averages are an interesting metric to read. They become super useful when you need to see how your machine is doing over a certain period of time. We won't get into load averages here, but you should read about them in the next supplemental reading. Another command that you can use to help manage processes is the lsof command. Let's say you have a USB drive connected to your machine. You're working with some of the files on the machine. Then when you go to eject the USB drive, you get an error saying device or resource busy. You've already checked that none of the files on the USB drive are in use or opened anywhere. Or so you think. Using the lsof command, you don't have to wonder. It lists open files and what processes are using them. This command is great for tracking down those pesky processes that are holding open files. One last thing to call out about hardware utilization is that you can monitor it separately from processes. If you just wanted to see how your CPU or memory was doing, you could use various commands to check their output. This isn't immediately useful to see on a single machine, but maybe in the future, if you manage a fleet of machines, you might want to think about monitoring the hardware utilization for all of your machines at once. We won't discuss how to do this, but you can read more about it in the supplemental reading. You've done some really great work in this module. You learned a lot about how to read process information and manage processes, something that will be vital for you to know when troubleshooting issues as an IT support specialist. The next assessments will test you on that new process management knowledge. Then, drumroll please, we'll be on to the last and final lesson of this course. We'll cover some of the essential tools that are used in the role of an IT support specialist.